So the next couple of sections, 5.2 and 5.3, are on specific distributions. The binomial and Poisson distributions are really families of distributions. So what's the idea of these, what are sometimes called canonical distributions? There's something on my trackpad over here. There we go. What's the idea of these canonical distributions? Well, you can imagine that we had, I don't know, say some kind of imbalanced die. Like this, right? If I have a die and I figure out that the faces come up with these probabilities, I can do analysis of this distribution. I can figure out its mean. I can figure out its variance or standard deviation. Maybe figure out different probabilities related to odd numbers or even numbers or whatever it may be. And that's really nice to know maybe about that die, but if I move to a different die or a different scenario, I really can't use any of that information, right? I just have to start from scratch all over again. But what if I had something that was a little more general? What if I developed a distribution where, provided that I satisfy a couple assumptions, I can figure out what the rules for the distribution are, and then I know anytime in the future that I see a scenario that satisfies those assumptions, I can just apply the rules. I can essentially know immediately what the mean is, what the standard deviation is, how to compute probabilities. That's the idea of canonical distributions. So in discrete distributions, we have a couple of famous ones. The most famous is binomial. Poisson is also somewhat famous. There are some others as well, like the geometric distribution is another pretty common one. And these are distributions that they basically say if you satisfy certain assumptions, then your probability distribution will be distributed according to these rules, according to this, say, mathematical formula. And then we can compute things like the mean or the standard deviation for that distribution. And what that does is, in the future, if we look at a problem, we recognize it as a binomial problem, then we pretty much immediately know what its mean and what its standard deviation are. We don't have to go through writing out all of the outcomes, writing out all their probabilities, doing the whole chart. We can just use a formula and figure out what's the mean, what's the standard deviation, or maybe what's a certain probability. And we wouldn't have to go through the hassle of doing all the counting and all of those kind of things. Okay, so binomial distribution has some assumptions. So the first is that we have a fixed number of trials n. So the classic example for a binomial distribution is something like flipping a coin n times. So say we flip a coin 10 times. There are 2 outcomes per trial, success or failure. And this is just success in the sense that did we find the thing we're looking for? So it's not meant to imply any kind of moral value or anything, right? I mean, if you're doing, medical research or something, success might be that the person has cancer because you're counting the number of people who have cancer. So it's not, necessarily implying a good thing or a positive thing, but just success in that we were looking for something. Did we succeed in finding it in this case or not? So if we were counting the number of heads on 10 flips of a coin, success might be getting a heads and failure might be getting a tails. So we have a dichotomous event, success or failure. Note that that doesn't mean that there are only 2 outcomes. We could roll a die and have success or failure. We could be looking for an even number, and we could either get an even number or not get an even number. We could be saying, well, maybe I'm looking for, did I roll a 1? I either rolled a 1 or I did not roll a 1, right? So this is maybe more general than it seems at first. There's independence between trials, so knowing that I succeeded on the first or the 7th or the 3rd trial shouldn't affect my estimate of succeeding on any of the other trials. And the probability of success stays the same across all trials. we typically call the number of trials n. Let me change this to, there we go. We typically call the number of trials n and the probability of success on an individual trial p. So in our coin flip example, if we flip the coin 10 times, n would be 10 because that's the number of flips that we're doing. If we're looking for heads, if we decide to label success as heads, then probability of success or probability of heads would be p. So if I thought this was an unfair coin where heads came up 70% of the time, p would be 0.7. That, of course, implies, because there are only two outcomes, success or failure, the probability of failure has to be 1 minus p because those probabilities have to add to 1. And often we give probability of failure the label q. So probability of success p, probability of failure q, p plus q equals 1. And if we let the random variable x be the number of successes on n trials, then we can say the following. If the assumptions are satisfied, if these four assumptions are satisfied, then we say that x is a binomially distributed random variable with parameters n and p. And we write it this way, x tilde binomial or binom or bin or something like that, parentheses np. So this is saying that it's a binomially distributed random variable because it satisfies these assumptions with parameters n and p. So this is a family of distributions. If we change n or we change p, we get a different distribution, but that allows us to fit a lot of different scenarios, right? If you were flipping the coin with probability of heads 70% 10 times, that's one particular binomial distribution where n is 10 and p is 0.7. And if somebody else was flipping a fair coin 6 times, that's a different binomial distribution. N is 6, p is 0.5. And the idea is that the results that we'll derive about x, about the binomial distribution, can be readily applied to either of those two scenarios or a myriad of other scenarios that fit this model. So that these two people or anybody else wanting to use this wouldn't have to go through from first principles using the chart and compute, say, their mean or their standard deviation. They could get away with just using a formula. So first, let's find the probability x equals k for allowable k's. Now, what could k be? What do my outcomes of x look like? Well, I have a fixed number of trials n, and I'm counting the number of successes on n trials, or something like the number of heads on 10 flips of a coin, right? I could imagine getting 1 or 2 or 3 heads on 10 flips of a coin. I could get up to 10 heads on 10 flips of a coin. Be careful that we could also get 0 successes, right? We could get 10 tails. That's one that's easy to forget. So k actually can go anywhere from 0 through n, right? We could get 0 successes on n tries, or say 0 heads on 10 flips, all the way up through 10 heads on 10 flips, and any integer in between. So consider the chapter 4 idea where we want to set up outcomes that are equally likely. So let's consider a given sequence of k successes that would have n minus k failures. And for that sequence, let's say, if we want 3 heads on 5 flips, maybe the particular sequence we're interested in is heads, tails, heads, tails, heads. For that sequence, what's the probability that sequence occurs? Well, that means if I wanted to do this sequence, what's the probability of that? Well, really what that means is probability of heads on flip 1 and tails on flip 2 and heads on flip 3 and tails on flip 4 and heads on flip 5, right? That's really what this means. It's a whole bunch of ands connecting all of these. Slot 1 is a head, and slot 2 is a tails, and so on. But remember, I have independence. We love independence because that lets us split lots of things apart, like we just saw. Well, this is just probability of heads on flip 1 times probability of tails on flip 2, and so on. And maybe I will write them out. Let me bump this down a couple of notches. But I noticed that probability of getting heads on flip 1, my probability of getting a heads is the same for all trials. So this is P. Same with this one, and same with that one. And probability of getting tails, probability of failing to get a heads is Q. I see this as P cubed times Q squared. Or it's the probability of success to the power number of successes times probability of failure to the power number of failures. So this given sequence of k successes and n minus k failures occurs with probability of success to the number of successes, p to the k, times probability of failure to the power number of failures, q to the n minus k. If I get k successes on n trials, I have to get n minus k failures, right? So each such sequence has probability p to the k, q to the n minus k. How many distinct sequences are there that would have the same number of successes on n trials? So if I'm just asking about what's the probability of flipping 3 heads on 5 trials, does order matter here? Well, no, order doesn't matter. So if I counted each sequence distinctly, that's kind of where order matters. But then I want to include, say, all of the, for instance, 3 heads on 5 flips sequences. So heads, 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 tails, tails, or tails, tails, heads, 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 or any of these. I want to include them under the same umbrella. So how many different sequences are there? How many different unique sequences are there that have the same total number of successes? So moving from order matters to order does not matter. Well, remember, there are n choose k such sequences. Another way of thinking about this is I have n slots. In this example up here, I have 5 slots. And I want to fill in k, or in this example, 3 of them with heads, leaving the other 2 for tails. How many ways can I pick which 3 slots of these 5 I want to fill in with heads? Well, that's n choose k. So there are n choose k number of sequences with this probability that satisfy the event. So the probability of the event occurring, the probability of getting k successes on n trials is n choose k times p to the k times q to the n minus k. So this looks like a big scary formula, but if you understand where each of the components comes from, I think it makes a lot of sense. This counts the number of unique sequences that satisfies having the same number total of successes. This is probability of success to the power number of successes. And this is probability of failure to the power number of failures. Give me 1 sec here. Okay, so let's Let's look at a special case of the binomial distribution. In particular, the binomial distribution with just one trial. So counting the number of heads, for instance, on one flip of a coin. We have a special name for this. We call it a Bernoulli distribution. So binomial with one trial when n is 1, really the only free variable, the only free parameter is p. So we call this a Bernoulli distribution with parameter p, probability of success. This is a random variable that results in 0. So we're counting the number of successes, so we could get 0 successes. Well, the only way to get that is if we got one failure. That would be with probability q, or 1 minus p. And 1, we'd get one success on one trial with probability p, probability of success. We can realize that x above, the binomial number of successes on n trials, that's really just the sum of Bernoulli trials, right? In particular, the sum of independent Bernoulli trials. So if I have 10 flips of a coin, I can look at that as a sequence of 10 flips, or I can look at that as 10 individual trials, a first Bernoulli trial, a second Bernoulli trial, and so on. Let's think about the Bernoulli random variables for a minute. What's the expected value of a Bernoulli random variable? What's the expected value of a random variable that comes up? Let's maybe call this y. What's the expected value of this variable? Well, that's 0 times 1 minus p plus 1 times p is p. So in other words, if your coin comes up head 70% of the time, on average, you expect to get 0.7 heads per flip. What's the variance? Well, that's expected value of b squared minus the square of the mean. So if I square my y's, I get 0 and 1 again. 0 squared is 0, 1 squared is 1. And then if I multiply across, I get just p. It turns out to be the same as the expected value. So that's expected value of Bernoulli squared minus the square of the mean, minus p squared. That's p times 1 minus p, that is pq. So a single Bernoulli trial has expected value of p and a standard deviation, or sorry, a variance of pq, standard deviation of root pq. So then what's the expected value of x of the binomial where we have a sequence of n Bernoulli trials? If I even just asked you, okay, on 10 flips of a coin, where heads comes up 70% of the time, how many heads do you expect to get on 10 flips of a coin? I think most people would just intuitively say, oh, probably 7, right? They just say, okay, 70% chance per flip and 10 flips, so probably about 7 heads on 10 flips, so it would be reasonable. And it turns out that that intuition is not wrong. So the expected value of x, expected value of the binomial, where we have n Bernoulli trials, is the expected value of the sum of the n Bernoulli trials. But remember, expected value just splits sums apart. So that's expected value of Bernoulli trial 1, and so on out through, plus expected value of Bernoulli trial n, or that's just p added to itself, right? That's just p added to itself n times, that's n times p. So the expected value of a binomial distribution with n trials, p probability of success per trial, is n times p. What's the variance for the binomial distribution? The variance for x is, again, the variance of the sum of the Bernoullis But remember, what we just showed is that if we have independence, variance is split sums apart. So that's variance of Bernoulli 1 plus variance of Bernoulli 2, and so on through plus variance of Bernoulli n. But what's the variance of a Bernoulli trial? PQ. Or that's PQ added to itself n times. So the variance for a binomial, which is what we found here, a sequence of Bernoulli trials, the variance for a binomial is NPQ, and the standard deviation for a binomial is root NPQ. So to recap, if I'm in a situation, if I have a problem where these four assumptions are satisfied, if I can figure out N and P from my problem statement, then I basically get all of this for free. I can figure out probabilities using a formula. I can figure out the mean and the standard deviation using two formulas. I don't have to draw out a whole chart. I don't have to build off all those columns and do all the calculations. I can just use these formulas whenever these assumptions are satisfied. And there are a lot of important applications where these assumptions are satisfied, or at the very least, we can reasonably suppose they're satisfied. So maybe independence, we might say, well, when we're overlaying this model into the real world, is independence ever always true? Well, probably not, but is it close enough that we can reasonably assume it as part of the model, or reasonably assume that that part of the model is a decent representation of reality? Often that's true. Okay, so let's do an example. Let's look at the number of heads on 5 flips of a fair coin, and let's let the random variable x. Some of my variables here. Oh, some of my variables here lost their formatting for some reason. Let's let x represent the number of heads on 5 flips of a fair coin. We want to find the probability distribution for x and its expected value and standard deviation. So here I'm going to be a little more pedantic, and I'm going to, typically I would write x and probability of x, but that's really kind of a shorthand for really writing the outcome k, 0, 1, 2, 3, 4, 5, and then the probability that the random variable equals that outcome, probability x equals k. I'm being a little pedantic here because if I just wrote probability of x up here equals this, it might not be clear exactly where this k is coming from. But this notation, I think, makes it clear. We're saying the probability that the random variable equals some number that's one of its potential outcomes. So let's work on k equals 0. So what's the probability x equals 0? Well, I see the first thing I need to do in any binomial problem is, well, number one, let's make sure the assumptions are satisfied. And then number two, let's find n and p. So what were the assumptions? Fixed number of trials, 5 flips of a coin. Yeah, that's a fixed number. 2 outcomes per trial, success or failure. Yeah, we either get a heads or we don't get a heads. Independence, I think that's pretty reasonable to assume on things like coin flips, that knowing I got a head on one of the flips doesn't impact my estimate of how likely it is to get a head on any other flip. And the probability of success stays the same for all trials. Yeah, probability of heads is 50-50 for each of these. So n is the number of trials. And p is the probability of success per trial. And it's 0.5. So I verify that the assumptions hold. I found n and p. Now I can say that probability x equals 0 is n is 5, choose 0, k is the outcome we're interested in, times p to the k, 0.5 to the 0 power, if P is 0.5, that tells me that Q 1 minus 0.5 is also 0.5, right? 50-50 chance of getting a heads or tails. And 0.5 to the power n minus k, well, n minus k, 5 minus 0 is 5. Well, 5 choose 0 is 1. If I have, say, a bag and a box, and my bag has 5 outcomes in it, and I want to choose 0 of them and put them into the box, and neither of the two are ordered, there's only one way to do that. I just leave them all in the bag. 0.5 to the 0 power is 1. And then times 0.5 to the 5th, or this will be what? 1/32. 0.5 is 1/2, so that's 1/2 to the 5th. That's 1/32. Now, what about when k equals 1? Well, what do? Everywhere I see a k, I just increment it. 5 choose 1. Oh, how did I get a triangle out of that? 5 choose 1. I now have 1 success and 4 failures. But I note that this is still 1/2 to the 5th, right? So this still ends up being 1/2 to the 5th, because swapping a heads for a tails, I'm taking one of the 0.5s away, but sticking in another 0.5. That swap doesn't affect this probability at the end here. But I do note that if I have a bag of 5 outcomes, how many ways can I choose? 1 and put it into the box on the other side. Well, there's 5 ways to do that, right? 5 choose 1 is 5. Now, what if I looked at, say, k equals 4? Probability x equals 4, or this is 5 choose 4. 0.5 probability of success to the number of successes, 4, times probability of failure to the number of failures, 1. What's 5 choose 4? Well, that's if I have 5 items in my bag and I want to pull 4 out and put them in the box, and both bag and box are unordered. Well, the number of ways to choose 4 outcomes from 5 out of the bag is the number of ways to choose which one to leave in the bag. So that's a nice symmetric problem. I see that that's got to be 5. And then, because the probability of success and probability of failure are equal, this is also 1/2 to the 5th. This is 5/32. What about k equals 5? Again, those two multiplied together gives me 1/2 to the 5th, or 1/32. If I have 5 objects in the bag, how many ways are there for me to take all 5 objects out and put them in a box, leave them unordered? Only one way, of course. And then these two probabilities multiplied together give me 1/32. Right? This is just indicating the sequence tails, 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 tails. This is heads, 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 heads. And then this like 5/32 would be like, to get 1 head on 5 flips, heads could be in the, or, oh, I did that backwards. This is all the tails. So for k equals 1, that's heads can be in the first place, or it can be in the second, or third, or fourth, or fifth place. Those are the 5 different ways we could get 1 heads. So I think we can probably see that for k equals 2 and k equals 3, there should be a symmetry there as well. 2 heads versus 3 tails versus 2 tails versus 3 heads. That should be symmetric as well. We could do something like say, okay, we have 6 30 seconds plus 6 30 seconds is 12 30 seconds accounted for. That leaves 20 30 seconds to be accounted for still. Maybe we would guess that by symmetry, these should both be 10 30 seconds. Let's just check that. These two factors still make 1/2 to the 5th. But let's just check. Let me see. Get a little more room over here. Let's check, what does 5 choose 2? This is 5 factorial over, oops, that should be a 2 factorial. 5 factorial over 2 factorial times 3 factorial. But 5 factorial is 5 times 4 times 3 factorial. So those will cancel. 5 times 4 is 20. 2 factorial is just 2 times 1 is 2. You get 10. We do indeed get 10 30 seconds for k equals 2. And then, of course, at this point, our kind of guess of symmetry is confirmed. We can get the k equals 3 by the probability rule that all the probabilities have to add to 1. We have to add up to 32 30 seconds. And the only way to make that happen is that probability k equals 3 has to be 10 30 seconds. So note the symmetry here. We have nice symmetry with the combination, as well as when we swap a head for a tail. So because heads and tails are equally likely, if I allocate, 3 heads to the bag and 2 tails to the box, versus if I put two heads in the box and 3 tails in the bag, whichever way I said it, the opposite of what I said it last time. If I do it one way or the other, it's really the same question. It's just the way to split 5 things into 3 versus 2, keeping those unordered. Whether it's 3 versus 2 or 2 versus 3 is somewhat irrelevant because the probabilities are the same. How would this change if the coin is unfair? Well, let's jump over to Excel. Let's try to replicate this on Excel. And then maybe we'll investigate what happens if the coin is unfair. So I'm going to make 2 cells down here. P is 0.5 and N is 5. And let's make our probability distribution. Now we could do something like this, equals COMBIN. That's our N choose K, our combinations function. And I want to use N, the number, choose K, 0. Let's check that that works, and that does end up being 1. Now I do want to drag this down, but I see this does increment K, which is what I wanted to do, but as I have it now, it also increments this cell for N. I don't want it to do that. So the cell related to N equals 5, I want to lock that using F4 or Command T if you're on a Mac. And here I see that symmetry of the combination function. Now this isn't the probability yet. We've only done this part, but I just want to point out that symmetry there. There's one way to get 0 heads on 5 flips. You got to get all tails. there's 5 ways to get 1 head on 5 flips. Heads can go in the first slot or the second or third or fourth or the 5th slot. 2 and 3, it's a little harder to count, but there will be 10 ways to get each of those. So we have this nice symmetry. Now, what do I want? I want n choose k times p to the k. I want my p to stay locked to the power k times 1 minus p. I want that to stay locked as well to the power n. I want that to stay locked as well minus k. It's a bit to type in. And if I did this, I see 1 30-second, 5 30-seconds, 10 30-seconds. I see that I get those same numbers, right? If I didn't want to type all of this in, because it is kind of a pain, and if you're not used to doing this kind of stuff, it's very easy to miss a parentheses or get a parentheses in the wrong place, or forget to lock a certain cell, or lock a cell that you shouldn't lock. I could instead use the built-in function binomial distribution, binom.dist. And I want to enter a few different things. Here I want to enter the number of successes. The number of successes I'm interested in finding the probability for is just my k number here. I don't want to lock that because I want that to change as I drag it down. What's the number of trials? N equals 5. I do want to lock that because as I drag this down, the trial should stay at 5. What's the probability of success? Probability underscore S. That's P. Again, I want to lock that because I want that to stay the same from line to line. And cumulative, well, cumulative means, am I asking for something like probability X less than or equal to K? Remember, that was what we said. It was a cumulative probability distribution. No, I don't want cumulative. So I'll do false. You could just type in false, or you could pick it from the dropdown. I don't want it to be cumulative. I'm not asking a question like, what's probability X less than or equal to 1? I'm asking what's probability X equals 1. And you see that we get the same answer either way we did it. So obviously quite a bit easier to type in this and use all of the prompts than to try to type it in from first principles. Now, what if I change P? Does this still stay symmetric? Well, no, it doesn't, right? 0.002, 0.02, 0.13, 0.30, 0.36, 0.16. We've lost that symmetry. The combination is still symmetric. If I say how many ways are there to split 5 things into a group of 3 versus a group of 2, that's the same question as splitting into a group of 2 versus a group of 3. But the thing is now, if I want to pull out 3 items and put them into the box, or if I want to pull out 2 items and put them into the box, it's either more or less likely that I get 3 or 2 of this thing, right? In other words, getting more heads when heads is likely is kind of easier to do than getting more tails when heads is more likely. So it's more likely that I get a high number of heads when heads is more likely than the tails, then I get a high number of tails. So by having an unfair coin, I've broken my symmetry. But again, with a fair coin, that maintains that symmetry. The combination has a symmetry in a fair coin. Since probability of heads and probability of tails are the same, I keep that symmetry. But if I change my probability of heads to something other than 0.5, I lose the symmetry. What's my expected value of X? Well, remember, that's N P. This also kind of makes sense, right? when the expected value is 0.5, or sorry, when P is 0.5, the expected value is 2.5, right in the middle of the distribution, kind of in correspondence with that symmetry. But when P is, say, 0.7, I'd expect my expected value to be higher. The average number of heads per flip for 5 flips is going to be higher if heads are more likely to occur. And it wouldn't make sense for me to still have symmetry about 2 and 3, right? Because now I've moved the kind of the hump of the distribution, or the more likely bit of the distribution, off to the right. I've moved it closer to x equals 5. If I did something even more extreme, like P equals 0.9, 90% chance of getting a heads, the expected value goes all the way up to 4.5, and now I see that almost all of the mass of my distribution is up near 4 or 5. Very little chance of getting 5 tails or 4 tails or something when heads occurs 90% of the time. I think we intuitively see that, and we see it experimentally here as well. Okay, so we get nice symmetry, but only when the coin is fair. When the coin is unfair, when these probabilities don't function this particular way, when it's no longer the case that when I swap a heads for a tails, I'm just replacing one factor with the same factor, then I lose the symmetry, right? If this was 0.7 and 0.3, if I swap between these two, 0.7 to the first, 0.3 to the fourth, I've lost the 0.3, but I've gained a factor of 0.7. That's clearly going to change the result, right? Okay, so let's look at a second example in binomial. Suppose we have a quiz with 10 multiple choice problems, and there are 5 options per problem and 1 correct option for each problem. So let's look at a few scenarios. Let's suppose that a student just picks randomly. So they didn't study, didn't show up for class or anything, and they don't have any idea what they're doing. They just randomly choose all of their answers. What's the probability the student gets an 8 or more out of 10? It's the probability they get a good grade. Well, let's see it. If they choose randomly, are my assumptions satisfied? Do I have a fixed number of trials? Well, yeah, there's 10 trials. There are 10 questions that they're answering. Each one has a success or failure. They either answer correct or incorrect. Is there independence between trials? Well, if they're choosing randomly, I think there is. And is the probability of success the same for the trials? Yeah, there's 5 options for each trial or for each question. So it's not like some questions have 2 options and some have 5 and some have 10 options or something. They all have 5 options. If the student is choosing randomly, probability they randomly get the correct answer is 1 in 5 for each question. So this does seem like it satisfies the binomial assumptions. We want to find the mean and standard deviation. Well, we need to find n and p. So there are 10 problems. So there's 10 independent trials. And p, the probability of success, the probability of a correct answer on a given question, is 1 in 5. And we'll let x be the total number of answers correct on 10 tries on this test or this quiz. Expected value of x is np. On average, they get 2 answers correct. And what's the standard deviation of the number of correct answers? Remember, that's root npq. N is 10, p is 1/5. P is the probability of success, q is the probability of failure, so that's 1 minus p, or 4/5. And so what does this give me? It gives me root 10 times root 4 over 25. Well, that's just 2/5. So I need root 10, and then 2/5 is 0.4. So that's about 1.26. Call it 1.3. If I was kind of just very roughly, say, using the empirical normal rule or some of these ideas from the end of chapter 3, if I think that plus or minus 2 standard deviations away from the mean is kind of reasonable expectations for what could happen in something like this, well, the mean of 2, we could go plus or minus 2 standard deviations. So let's say plus or minus 3-ish. So somewhere between 0 and 5 is going to be a likely result for this student. What's the probability they get 8 or more correct? I think that's going to be quite small based on just that very rough heuristic. Mean plus or minus 2 standard deviations is kind of, reasonable, a reasonable event to happen. I think that's going to be quite small. If I wanted to actually check this, it's going to be kind of tedious to check by hand, right? I needed to figure out the probability they get 8 correct, the probability they get 9, the probability they get 10. I need to do 3 probability calculations, each of which has a combination times 2 probabilities. For something like this, I think I'll jump over to Excel to help out. So let's just kind of steal all of this, just make a copy of it. So here I want K to go from 0 to 10 because the student could, in theory, get anywhere from 0 answers correct to all 10 correct. My P, my probability of a correct answer on a given trial is going to be 0.2, right? 1/5. 1 correct answer out of 5 options per problem, and they're guessing completely randomly. N here is 10. I find my expected value to be 2. And square root of n times p times 1 minus p. That's that 1.3 or so. All right, what do I have wrong here? Oh, I locked these cells. I need to change what cells I'm referring to. So I need the binomial distribution. Number of successes is the K column. Number of trials now is this. Oh, didn't like that for some reason. Number of trials is N down here. And I want to use F4 to lock that. Probability of success in a given trial, that's P. I want to use this cell, F16 here. Use F4 to lock that. And now what's the probability that they get 8 or more correct? It's the sum of these probabilities. We can see that this is going to be quite low. 10 to the minus 5, 10 to the minus 6, 10 to the minus 7. Even if we added those up, it's still going to be extremely small chance. So 7 times 10 to the minus 5, let's just call that 10 to the minus 4. Well, what's that, like 1 in 10,000? So not very likely that they'll get a good score on this test. So now let's suppose that the student studied a little bit and they can narrow down the choices for each problem to 3 possibilities. So, quite often on a multiple choice test, you have, a few reasonable answers and then a couple that are kind of absurd that if you know a little bit about the topic, you can weed out a couple of the wrong answers. So let's suppose that for each problem, they can narrow it down to 3 possibilities instead of 5, but then they pick randomly between these 3. So we still have 10 trials, but now the probability of success on a given trial and a given answer is 1/3. instead of 1/5. So the probability of success goes up a little bit. So what's the mean of standard deviation? Well, let's come over to Excel. So n is 10, but now probability is 1/3. So we see that their expected value is now 1.3 or so. Their standard deviation has actually gone up a little bit from, say, what was it, 1.26 or something to 1.49. Remember before when we discussed that P of 0.5 gives the highest standard deviation? So we talked about that at the end of section 5.1. So again, kind of our rough heuristic mean plus or minus 2 standard deviations maybe is in the realm of reasonable possibilities. So 3.3 plus or minus about 3. So somewhere a little bit above 0 to something like 6 or 7 would be reasonable possibilities. What's the probability that they get 8 or more correct? Well, that's the sum of these three. I guess I should have just left that in. So it's 0.3%, or what would that be? Well, 1% is 1 in 100. 0.3% is about 1/3 of a percent. So that's about 1 in 300 chance that they get a good score on this test, that they kind of get lucky with their answers. But let's look at a third scenario. Suppose this student, studied a decent bit, but was struggling a little bit, and they know the answer for 5 of the problems. So 5 of the problems, they know what the answer is. They're sure they got the answer for that one. But the remaining 5, let's say that they know a little more, they can narrow down the possibilities to 2 choices each, and then they choose randomly between the 2. What's the mean and standard deviation for the number of correct answers? And then what's the probability they get 8 or more correct? So let's let y be the number correct. Well, what is y? Well, the number correct is the 5 that we know we got correct plus a random variable, right? Y equals 5 plus x. We know we got these 5 correct. That's not random. And then x, these are the ones we might or might not have gotten correct. We're not sure. How many questions did I guess on? Well, x is a binomial, where I guessed on 5 questions. So I was able to narrow it down to one of 2 choices for each of those. So what's the mean and standard deviation of the number of, oh, my internet connection is unstable. Hopefully I'm not breaking up on your end. What's the mean and standard deviation of the number of correct answers? What's the expected value of y? Well, that's the expected value of 5 plus x. Remember, expected value breaks sums apart, and the expected value of a constant is just that constant. So this is 5 plus NP. Or expected value of 7.5. Let's do the variance. The variance of y is the variance of 5 plus x. But we talked about variances before. Remember that the variance of a random variable plus a constant, the constant actually just goes away. We had talked about that in 5.1. So if you don't remember that, look back at those details. But that's just the variance of x, which is just NPQ. 5 times P, 0.5, times 1 minus P, which is 0.5. Or the standard deviation is the square root of NPQ, or that's 1/2 root 5. Or let's see what that is. Root 5 over 2 is about 1.1 or so. So do I think that getting 8 or more answers correct is reasonable for this student? Yeah, definitely. My realm of reasonable possibilities is kind of mean plus or minus 2 standard deviations. So 7.5 plus or minus 2-ish. Yeah, that's, 5.5 to 9.5. 8 or more is definitely in the realm of possibilities here. Or I could look at, for the questions I'm not sure of those 5 questions, there are 5 of them that we're guessing at, and probability of 0.5 of success for each of those. Now my number correct is 5 plus this. So I get 8, 9, or 10 correct in these 3 situations. And it turns out we recover this symmetry, interestingly, but it turns out that we have a 50% chance of getting 8, 9, or 10 correct. Right. We recovered that nice symmetry here. So 50% chance of getting 8, 9, or 10 correct. Any questions on anything so far? So we're really making use of all of those, that kind of dry background probability stuff that we talked about. But we're really leveraging that here, right? I mean, to figure out our formulas for the binomial, we needed those ideas. But even in this example, we used them directly. The properties for expected value and variance here, we used them directly for this example, to be able to analyze what happens when we kind of know that we got 5 right and 5 are random. Does that, knowing that we got 5 right, does that affect the expected value? Well, yeah, it does. It just adds 5. We probably could have guessed that. But I think it would have been harder to say, well, knowing that I got 5 right, should that affect the variance? I think if I had asked you that and we didn't have this background, I think I'd have been confused. I'd have had to think about it. Say, wait, does that affect the variance or not, right? But we saw that having that background, knowing how adding a constant onto a variance affects it, it doesn't affect it at all. That just let us answer this pretty quickly. Okay, so that is the binomial distribution. We have another distribution that's a canonical distribution. There are tons and tons of these distributions, by the way. Maybe I shouldn't say tons, but there are many of these that are popular where the assumptions kind of lead widely analyzed. So another one I mentioned is like geometric distribution, but there's also some like hypergeometric distribution and all kinds of different ones. So what's the idea of the Poisson distribution? And I'm butchering the French, so sorry if any of you are French, but I think Poisson actually means like fish in French. So, but this is named after a guy whose last name was Poisson, not after a fish. So Poisson or something like that. So what's the idea of this distribution? Well, this can be used to model counting phenomena. So if I want to count the number of occurrences of an event in a specified time period or some specified interval of some type, typically we think of a time period, but it could be something else. Could be like number of typos on a page or something like that, or within a certain number of pages of a book, something like that. Kind of the heuristic, the rule of thumb of when a Poisson makes a good distribution or is a good distribution to use is if the phenomenon is kind of rare, if it doesn't occur very many times in a given time period, yeah, kind of on average. And what are the assumptions for Poisson? X is the number of occurrences of an event in some specified interval. Note that unlike binomial, we don't have a fixed number of trials. So how big could X be? You know, how many typos could there be in a page? Well, is 10 the max that you could have? Well, why couldn't you have 11, right? What are the number of like phone calls that come into a call center in an hour? Well, maybe it's usually, less than 20, but could it be 100? Well, sure, why not? That if we're just counting the number that occur in some interval, we don't really have an upper bound. So that's the first thing that adds a little complexity to Poisson that we didn't see in binomial. The occurrences are random, and the occurrences are uniformly distributed over the interval, and are independent of each other. So if I was in a call center, would I want to say that, over an entire day or over an entire week, I think that a Poisson distribution should apply? Probably not, because there's obviously going to be heavier call volume times and lower call volume times. But maybe over a given hour or something on a particular day, maybe this could reasonably occur. Poisson, for some reason, your book, I think, says that the Poisson parameter is mu. It doesn't particularly matter what we call a parameter, but like everybody calls the Poisson parameter lambda. So I'm going to call it lambda. If it bugs you and you want to call it mu, you can call it mu, but this is lambda. This is the Greek letter L, small letter L. So you might have seen lambda in, it's often used for wavelength, for things like wavelength of light or sound or something like that in physics or chemistry. So you might have seen lambda used there as well. So if X is Poisson distributed with parameter lambda, then its calculation for probability is this: lambda to the k power over k factorial. So as k changes, lambda to the k power changes and k factorial changes, times e to the minus lambda. E to the minus lambda does not change. It's a constant that does not change as we change k, but it would change if we change the parameter lambda. Here, e is a number. It's a number that's approximately 2.71828. And the allowable k's, the allowable outcomes for x, are any non-negative integer. So 0, 1, 2, a million, a billion, 10 to the 10th. Those are all allowable k's. What does lambda represent? It represents the mean number of occurrences of the event that we're interested in the specified time interval. So we need to specify a time interval that we're talking about, and then we can figure out what lambda is. But we need to specify the time interval first. It's a little bit like units, like, if the information is given to you in meters, but you're interested in knowing the answer in kilometers, well, you kind of have to convert to the same units. So we have to decide on a time interval that we're interested in, and then make sure that all the information is given to us in that same time interval. So if information is given to us in terms of so many occurrences per hour, but we're interested in occurrences per day or occurrences per minute or something, like, we might have to shift some things around. And therefore 1 over lambda represents the average time between occurrences, or the average interval amount between occurrences. As I kind of mentioned, this is a counting variable, so there's no upper bounds on the count on the outcomes. We can't write out the entire probability distribution. We can only write out a portion of it, right? So sometimes I denote that with like ... at the end, like this. And sometimes it's just like, okay, well, we understand that it's truncated, so this is how much we need to answer the question that we're trying to answer. But in practice, you might say, oh, well, what if I want to use this distribution to say model the number of typos on a page of text in a book? Well, could I have 100 billion typos on a page of text in a book? Well, of course not. But again, this is an issue of all models are wrong, some models are useful. This k factorial in the denominator, remember, these factorials grow very, very quickly. 70 factorial is already too big for the TI-89, or sorry, TI-83. So this k factorial in the bottom grows very, very quickly. It grows much faster than lambda to the k. We have a polynomial on the top and a factorial on the bottom. These probabilities are going to go to zero quite quickly. So with the probabilities going to zero that quickly, if I'm modeling something like typos on a page, okay, maybe I'm saying that technically there's some non-zero probability of getting a billion typos on a page, but it's so incredibly small that it's effectively meaningless. Okay, so let's go back to the Poisson distribution. And just a quick recap, because it was last week when we talked about this, the Poisson distribution is a counting model. So if we specify it, we'll typically call it a time period, but it could be any specified interval. It could be a distance or something like that, or say number of pages in a book or something along those lines. We might want to count the number of occurrences of an event in that time period, in that interval. Poisson is often used to model rare phenomena. So when we typically only see maybe 0, 1, or 2 or something instances of the event in a given time period. And we have some assumptions for Poisson. So effectively what Poisson is if we took a binomial distribution. So remember, a binomial distribution has n trials, each of which has a fixed probability of success, probability of being in the event we're looking for, p, and it has mean n times p. If we imagined increasing the number of trials, but keeping the product of n and p the same, so if we increase n, we have to decrease p. So if we double the number of trials, we have to have as in 1/2, we have to have the probability of success per trial. If we imagine doing more and more and more trials with smaller and smaller and smaller probability of success per trial, such that the mean stays the same as we increase number of trials and decrease probability per trial of success, that's actually how you can derive the Poisson distribution. So in a sense, the Poisson distribution is a limiting case of the binomial distribution. And we say if x is Poisson, if our random variable is distributed as a Poisson random variable with rate lambda, where lambda is the mean number of occurrences of the event per time period, the probability x equals k, the probability that our random variable equals k, so I'm counting numbers 0, 1, 2, etc., is given by this. Well, lambda to the k over k factorial times e to the minus lambda. Here e is a number. It's 2.71828. It's like pi. It never ends, it never repeats, but it's approximately 2.71828. And k is a counting number. So what's different from binomial is that k could, in theory, be 1,000,000 or 1,000,000,000, or there's no upper limit for k. So when we write out a probability distribution, we have to just write out a portion of it. The same way if I said, write out a tabular representation of y equals x squared, you can only write out some inputs and some outputs that is representative for the region over which we really care about that table. So for example, if we have a random variable that's distributed as Poisson with lambda equals 2. Oh, and by the way, I think the textbook uses mu for the parameter instead of lambda, but like pretty much everybody uses lambda, so we're going to use lambda. But if lambda equals 2, let's compute the probability that x equals 0, 1, 2, or 3. And we could keep going. We could ask for the probability x equals 4 or 10 or 100, but we'll just stop here. We'll say these are the ones we're interested in. So coming over to my calculator, I have, well, lambda is 2 to the power k to the 0. Over 0 factorial. I go into math, probability menu number 4, and then times e to the minus lambda. For e to the power, if you see next to 4, there's this button ln for natural log. Above that is e to the x. So I'll do second ln, giving me e to the power, and then a minus lambda or minus 2, or specifically -2, using the negative next to enter. And this gives me this about 0.135. Now notice when k increments from 0 to 1 or 1 to 2, lambda to the k over k factorial, that changes, but that e to the minus lambda does not change. So when I increment k from 0 to 1, I'll increment the power on lambda and the factorial and leave the rest alone. If I do second enter, that brings up my last entry. So for probability x equals 1, I need lambda to the 1, 2 to the first power, over 1 factorial, e to the minus lambda. For k equals 2, I need lambda squared over 2 factorial. So I'm incrementing the power on the top by 1, and the factorial on the bottom by 1. And this actually puts another factor of 2 on the top and another factor of 2 on the bottom. So it's going to actually turn out to be exactly the same as the previous one. That's kind of just coincidence. If we had a different lambda, or if we were going between, 2 to 3 or something, it wouldn't do that. And for k equals 3, I need lambda to the k, 2 to the third power, over 3 factorial, e to the minus lambda, so 0.180. If I wanted to do this a little more efficiently, let me clear all this junk out of here. If I want to do this more efficiently, and I don't need to do this, so if you're happy with doing it that way, if you say, okay, that that's the level that I want, you can stick there, that's not a problem. But if you wanted to do it a little more efficiently, you could type the formula in here as a function of a variable, and that variable will be the number of success, or the number of occurrences. So I want 2 to the power, the variable. Now the variable happens to be x. The x in the calculator is not the random variable x, it's just this general, it's the thing that we want to change. So the x in the calculator is actually the k in the formula over here. So 2 to the x over x factorial. I want x, go to my probability menu and get factorial, times e to the power. Remember that second ln, second natural log, gives me e to the power, minus 2, or -2. Usually it's a bit of pedantry whether you say -2 or -2, but here you actually do need to use the negative down here next to enter, or it'll give you an error. And instead of graphing this, we're going to use the second options up here, like the table set above window and the table above graph. So let's go second window, and let's start our table at 0. And let's increment our table by 1 so that our inputs will look like 0, 1, 2, 3, starting at 0, incrementing by 1. And then second graph, we'll bring up our table. So we see our inputs, 0, 1, 2, 3, with their corresponding outputs. So if we needed to find a few of these, it might be quicker to just go to the y equals menu, kind of type it in general, the formula, and then bring up our table, and the calculator will do a lot of the legwork in the background for us. Any questions so far?
Yeah,
Yep.
I just have one. I sort of was having difficulty trying to type an exclamation point on mine.
Oh yeah, yeah, definitely. So let me try that. There we go. So if we want to do factorial, like say 5 factorial, we just type in the number, and then we do math. In the math menu, we can just go left to go over to the probability submenu. And then you can either type 4 or you can go down to the factorial and hit enter.
Got it.
Okay, cool. Any other questions? All right, give me one sec here. Okay, so I think we did talk about this last time, that the expected value of a Poisson random variable is lambda, its parameter, and that the variance is also lambda, or sorry, the variance is also lambda, so the standard deviation is square root of lambda. I think we talked about this last time. If we didn't, it's not a big deal. If you're interested in the details, here they are. But I think just for time's sake, we'll skip over that. But the expected value and the variance are both lambda. So let's look at an example here. We have that a machine averages 3 breakdowns per month. We'll let X be the number of breakdowns in a given month for this machine. And let's assume that X is Poisson with rate lambda. Let's compute 2 probabilities: probability that X equals 2, the probability that in a specific month we get exactly 2 breakdowns. And let's compute probability X less than or equal to 1, probability that in a specific month we get less than or equal to 1 breakdown. So we see that lambda equals 3, which is the average number of occurrences per time period. So what does that tell us then? That tells us probability X equals K is lambda to the K over K factorial e to the minus lambda. So I need to compute this for K equals 0, 1, and 2. I need K equals 2 for this bit. And for X less than or equal to 1, X can only be 0 or 1. So I need those 2 outcomes probabilities as well. So if I go back to my y equals menu, I can reuse most of this. So I need 3 to the K instead of 2 to the K over K factorial. That stays the same, times e to the minus 3 instead of e to the minus 2. If I do second table, I see I get these numbers, right? 0.049 and so on. So I see the first answer, probability X equals 2, is just 0.224, 22.4% chance that we get exactly 2 breakdowns in a month. probability x less than or equal to 1 is probability x equals 0 or x equals 1, which of course is probability x equals 0 plus probability x equals 1. These are clearly mutually exclusive. So that's the sum of those two probabilities. So that's 19.92%. Any questions so far? Okay, let's look at another example. Let's suppose that that we own a small company and we're going to model the number of customer service calls within a time period. We choose a Poisson random variable for that. And the reason we care about this is we have a single customer service representative employed. Some industry standard, some benchmark says that if the average number of calls per hour exceeds 20, we should hire another representative. One representative can handle kind of an average of, let's say, 20 calls per hour. And we're interested in whether we ought to hire another representative. So we take a sample, we sit next to a representative for 15 minutes or something, and we see that there are 9 calls observed. And our question is, well, basically, do we think we should hire a new representative? Now, at first glance, we might say something like, okay, well, 9 calls in 15 minutes, that's 36 calls per hour on that sample. We might say that's bigger than 20, so yeah, we need to hire somebody else. But we also realize that calls are random, right? It might have happened that the 15 minutes that I sat there, we got a higher than average number of calls, and the next 15 minutes, maybe we got a much lower number of calls. And you might say, well, sit there for more than 15 minutes, but you could say the same thing about, if you watched for a day or for a week, is this a busier week or a less busy week, right? So one thing that we might want to do is we might want to say, okay, well, practically speaking, we might want to ask, do I think this is a representative sample? Those kind of things, right? So those would all be fair questions to ask, but let's just focus on the probability side of things at this point. So really what I'd like to know is, do I think this would be an unusual occurrence if the actual mean number of calls per hour was 20? So in other words, if the mean number of calls per hour was 20 and my customer service representative could handle that by themselves, occasionally there will be a busy time period. How likely is it to have such a busy time period, right? Or if the mean number was 30, then how likely is it to have a busy time period like this? Or if the mean was 15, how likely is it to have such a busy time period? And then we might want to take that data and try to answer the question with a little more understanding. Should we hire an additional operator? So let's use a time interval. "15 minutes or a quarter hour." So we observed 9 calls in 15 minutes. So let's let X be Poisson. We observed X equals 9. And we want to know, what's the probability X bigger than or equal to 9 under certain different values for lambda. Obviously, I can't count up all of these because X could be 10 or 11 or a million or a billion. But this is 1 minus probability. X is strictly less than 9. And this I should be able to calculate. It would be quite a pain to calculate it by hand, but maybe we can use a calculator or Excel and make it a little easier on ourselves. So for part A, if my mean was 20 calls per hour, that's equivalent to 5 calls per 15 minutes, 5 calls per quarter hour. So my question here is, if X is Poisson with rate 5, what's the probability X bigger than or equal to 9? Okay, so I think maybe to do this, we could do this on the calculator, but let's just bring up Excel just to show a different way of computing Poisson values. And let me zoom in a little bit here. So I'm going to have a column for the Ks and a column for probability X equals K. I know I'm interested in when X is strictly less than 9, which is 0 through 8. So this is the portion of the probability distribution I'm interested in. And of course, it would keep going after this, but I'm just truncating it here. I'm also interested in the sum of these probabilities, and in particular, 1 minus that sum. And this is the probability X bigger than or equal to 9. We want to be able to change lambda. And here we use 5, and this is calls per 15 minutes. So I want to be able to change this for parts B and C as well. So if X is Poisson with rate 5, then probability X equals K is what? Lambda to the K, or 5 to the K, over K factorial, e to the minus 5, e to the minus lambda. So I want equals, what I want lambda, this cell, I'm going to lock that because when I drag down, I want to keep that same reference to lambda for all of these probabilities 0 through 8. That's to the power K. In this case is 0. I don't want to lock that because when I drag down, I want that to pass by reference, or by relative reference, over K factorial. And here I don't want to just do exclamation point. We can see that it doesn't really understand what that is. I'll use the built-in function fact, F-A-C-T, factorial of K times E, well, that's the exponential function, the built-in function exp of negative lambda. Now that was kind of a lot to type in. We could type it in that way and get a number. We could also do equals Poisson.dist, Poisson distribution. And what is the X that we're interested in? What is the number of occurrences that we're interested in asking about? That's this number to the left, comma. What's the mean? The mean is this one. I want to lock this cell. So I use F4 or Command T to do that. And then cumulative. Am I asking for a Poisson am I asking for less than or equal to 1, or am I asking for just 1? Cumulative, false. I don't want cumulative. I could actually just do this in one line of Excel code and do cumulative true, but I think kind of working out all of the details is something that's probably helpful at this stage. So we could do this a little more efficiently, but so, and if we check one of these, we do see that we're still using the same lambda, which is what we want, and we are, you know, our probability is relating to the proper value of k. So I see these are the probabilities of getting 0 through 8 calls in 15 minutes when the mean number of calls for 15 minutes is 5. We see the probabilities around 5 are the most likely. Getting further away from 5 is a little less likely. And the probability that we end up with 9 or more calls is about 6%. So if lambda was 30 calls per hour, that's 30 over 4 calls per 15 minutes, 7.5. We see that lambda doesn't have to be an integer, right? K has to be an integer. For one, on one hand, we're trying to factorial it, so it kind of makes sense for it to be an integer. But on the other hand, just from the context, if our random variable is a counting number, it can only take on integer values. But lambda, the mean number of occurrences per time period, does not have to be an integer. So if lambda was 7.5 calls per 15 minutes or 30 calls per hour, we see the probability of observing 9 or more calls in 15 minutes would be about 33%. Or let's call it 34%. And on the other hand, if lambda was 15 calls per hour, or 3.75 calls per 15 minutes, the chance of observing 9 or more calls would be about 1.5%. So what are we doing here? We're actually using the idea of a probability distribution in reverse, kind of, to try to answer this question. In other words, on the basis of the observation of seeing 9 calls in 15 minutes, if I choose a Poisson model for my random variable, I'm not sure what lambda should be, right? I don't want to just set it at my little sample, 9 calls in 15 minutes. But I can ask, what's the chance of making such an observation under different models? When I have an average of 5 calls per 15 minutes, one 7.5 calls per 15 minutes, and one 3.75 calls per 15 minutes. And I see that B is much more likely than, say, A or C to result in this type of an observation. So in other words, do I feel confident that the mean number of calls per hour is actually below 20, maybe something like 15, and that we're good with just the one customer service representative? Probably not, because if our mean was, say, well below 20, well within the realm that one person could handle, if our mean was 15 calls per hour or 3.75 calls for 15 minutes, I would only expect to observe what I actually observed 1.5% of the time. It will be quite a strange occurrence, or quite an unusual event, that I chose that 15-minute period to watch over this person, and that type of 15-minute period only occurs, say, 1% or 1.5% of the time, or one time out of 60 or 100 or something. That would be quite strange, right? That's a bit of a stretch for me to argue that I think lambda's 15 calls per hour on the basis of what I actually observed. That seems to be discordant. On the other hand, it seems much more concordant to have a mean of something like 30 calls per hour. That makes what I observed much more likely. And so I think the data suggests that we should hire an additional operator, not just because of this kind of point estimate here, but also because of this analysis, right? That Now, hypothetically, we could imagine a situation where maybe, you know, for part A, we had gotten 10%, and for part B, we had gotten 12%, and for part C, we had gotten 8%. Well, now I can see, okay, this, if that was the case, this sample wouldn't be very informative for me to really understand what the actual average number of calls per hour is, right? If changing my mean number of calls per hour would result in a very minor change to the chance that I see such an event in my number of calls, then I'm thinking that maybe it's something more about the structure of the model. Maybe this is less informative. Maybe this piece of evidence is less informative about the mean than maybe my model is. I said that a little funny, but I hope that kind of makes sense. But given that we see such a big difference here, 1.5% to 6% to 34%, I think that we can say, okay, it seems that this piece of evidence gives us a good bit of information that about the mean, and I feel pretty confident saying that the mean number of calls per hour is actually bigger than 20. This wasn't just a chance occurrence where I happened to pick a really bad 15 minutes. But this is probably a regular occurrence. We should probably hire another operator.